Today, you are going to learn about fractals. Fractals are rough geometric shapes that you can divide into smaller parts, and each smaller part is going to be a rough copy of the whole. One of the first mathematicians to invent the fractal was named Gaston Julia. He lived from 1893 to 1978. He was a French fractal mathematician who created the formula for the Julia set using a complex number plane. After serving in the Second World War, he became a distinguished mathematician. Julia's work was forgotten until another mathematician named Benoit Mandelbrot brought Julia's work back into the limelight in the 1970s. Now on the screen are some examples of Julia's fractals. Much credit goes to Benoit Mandelbrot for the invention of the fractal, but many other mathematicians before him, such as Julia, were the ones who laid down the foundation of fractals. Mandelbrot, however, had a huge advantage over his predecessors because he could use technology. Mandelbrot is the father of fractal geometry. His fractals are the most popular nowadays. Like Julia, his fractals are also based on complex numbers. Now on the screen are some examples of Mandelbrot's fractals. Let us draw a fractal. To begin, we have an equilateral triangle. And what we're going to do is we're going to find the midpoint of each side, and we're going to connect the midpoints. Now we're going to find, again, the midpoints of each new segment. However, don't go too fast because we're not going to connect all of them. Here are the midpoints of the new segments formed. And here comes the tricky part. What you're going to do is you're going to connect the midpoints to form triangles. However, you will not connect the midpoints to form a triangle inside the center triangle. In this polygon, this triangle here is the center triangle, and we will not therefore connect these midpoints. We will connect the other midpoints to form other triangles. Again, we're going to find the midpoints. Brilliant. We have the midpoints. We're going to do the same thing. Connect the midpoints to form triangles, but do not connect the midpoints of this inside the center triangle. That's yet another iteration of this fractal. Now, let's take a closer look at this fractal. First off, if we look at one portion of this fractal, then we notice that it looks the same as the other portions. For example, this part of the fractal looks the same as this part of the fractal, which looks the same as the top part of the fractal, which looks the same as the larger triangle. Because even though there are some sub-triangles in the larger triangle, here's the larger triangle, and then here's the center triangle that's untouched, and then here are the triangles on the other sides. So this triangle is a well-known fractal, and it's called the Sierpinski triangle. And the Sierpinski triangle is one of my favorite fractals because it's really easy to see the pattern and how one subportion of the triangle is identical to the other portions. The Sierpinski triangle was discovered by the Polish mathematician Wacław Sierpinski in 1915 and has appeared in Italian art from the 13th century. Wacław Sierpinski was born in and studied in Warsaw. He lectured at various universities in Poland and Russia and received honorary doctorates from 10 universities. He became the vice president of the Polish Academy of Sciences and did very important work in 3 branches of math: number theory, set theory, and point set topology. Let's take a look at some fractals in nature. Here we have a tree, and if we look at this tree, we can see that if we look at one part of the branch, it's very similar to, if not the same, as another branch. And this is actually a special type of tree. Not all trees are this way, but a lot of them are. Now, let's take a look at 2 seashells. We look at the first one first. Then we can see that if you look at one portion, say this, it'll look the same as the corresponding portion on a larger scale, say that. And the same applies on the bottom. And as a bonus, this spiral happens to be the golden spiral. Here's a pineapple, my favorite fruit, and it also turns out to be a fractal. Because if you look at this portion looks the same as this portion, very roughly. And now this is actually a vegetable called the Roman cauliflower, or Romanesque. And if you look at this portion here, compared to this portion here, compared to this portion here, on a very rough scale of course, then you can see how all of this pattern is being repeated. And fractals in nature, just as a side note, tend to be much more rough than fractals like the Sierpinski triangle. Last but not least, we have the leaf. And the leaf is one of the more obvious fractals, because if you look at this stem, always has something going off of the left and the right sides, although they're not always aligned. So it's more of a rough fractal. And then these markings on the leaf, these smaller indentations, are quite similar, if not the same. We're going to take a look at the last fractal of this video, and that fractal is called a Koch snowflake. But before we do so, however, we have to learn a little bit about the Koch's curve from which the Koch snowflake is derived. The Koch's curve was invented by the mathematician Niels Fabian Helge von Koch, and he published the information about the Koch's curve in the paper Une méthode géométrique élémentaire pour l'étude de certaines questions de la théorie des courbes plans, which he published in 1906. And this curve has an infinite length. And von Koch also wrote on papers on the number theory and prime number theorem in the early 1900s. And now we're going to take a look at the fractal called the Koch snowflake, which is derived from the Koch curve. The way you make a Koch's curve is you start off with a segment, you divide it into thirds, and from the center segment you form an equilateral triangle. And then you erase the original base. So that middle segment, the center segment, you erase it. And then we use this to get the Koch snowflake. Here is a Koch snowflake in its iterations. This is the first iteration, the second, the third, the fourth, the fifth, and the sixth. If we try to figure out how many sides there are in each iteration, well, this is 3 in the first, 12 in the second, because for every one side, you get 4 sides, 1, 2, 3, 4. So we can say that the number of sides is equal to 3 times 4 to the power of the iteration. So the second iteration, 3 times 4 squared. To find the length of a side, if we look at this, if this side is x, then in this if this side is x, then in the second iteration, you're reducing the length by 1/3. See how because 1/3 of the side is erased. Therefore, the length of one side in the nth iteration would be x times 1 over 3 to the n power, or by property of exponentation, x times 3 to the negative n power. Now when we're talking lastly about the perimeter is equal to the number of sides times the length. If there's infinite sides, you get infinite perimeter. Because let's say there are 3 sides, then we'll call that perimeter p sub 0. If there are 12 sides, it's 4/3 of p sub 0. If there are 48 sides, 4/3 of p sub 1, which is 8/9 of p sub 0, which means that if there are infinite sides, then infinity perimeter. Before we begin finding the area of the Koch snowflake, we have to understand a couple of things first that we're actually going to use when finding the area of the Koch snowflake. So in an arithmetic sequence, you start with the first term, and you add a constant number to each term. So in this case, you do a 1 plus 2, 3 plus 2, 5, etc., all the way to 21. And then the number that you add is called the common difference. In a geometric sequence, you do the same thing as an arithmetic sequence, except you multiply. 2 times 3, 6, times 3, 18, etc., all the way to 4,374. Notice how in these two examples here, this example and this example, the sequence stopped. It just stopped at 21. It stopped at 4,374. If it's infinite, it can go on forever. And the way you denote infinity is you just put 3 dots at the end. And now a series, either arithmetic or geometric, is where instead of a comma, you have a plus sign. So then here, this is the same series, the same terms as this one, but you're adding them, and the same one over here with this geometric series, and that's the geometric sequence. And then if it's infinite, you can insert 3 dots at the end. And here, let's see now. If we have this example, you can see that ignoring the 1, this portion right here, this 1/2 plus a 4th plus an 8th plus a 16th, a half plus a 4th is 3/4, plus 1/8 is 7/8, plus 1/16 is 15/16, plus 1/32 would be 31/32, and then you can see how the sum is getting closer and closer to 1. So we would say here that this infinite geometric series, it has to be infinite, notice the 3 dots at the end, is converging to 1. And we can only say this if the absolute value of the common ratio is less than 1, meaning the number that we multiply by, the quote-unquote multiplier, has to be between -1 and 1, which is the case. It's a half. And now, you may be wondering, well, how do we find the sum of this infinite geometric series? Well, if this series is divergent, like this one, for example, where the common ratio is greater than 1, then the sum is infinite. But if it's convergent, we have a very convenient formula where the sum, S, is equal to the first term over 1 minus the multiplier. Let's take a look at one or two examples. So here, we have to find the sum of this series, and it is convergent, so we can use the formula. We know we can kind of look at it and guess that it's 2, but to prove it, we can use this formula, where the first term is 1 over 1 minus, then the multiplier is a half, because 1 times a half is a half times a half is a fourth, etc. So then we do the arithmetic, and we find that S is 2. You are going to solve a problem. So find the sum of the infinite geometric series 4/9 plus 4/9 squared plus 4/9 cube plus 4/9 to the fourth, etc. a hint? The first term and the multiplier are the same. This is okay. You should find that the answer is 4/5. Does anybody have any questions? We're now ready to show that the Koch snowflake has a finite area. We're going to have to compare the number of sides to the area of the figure when there are that many sides. If we have 3 sides in the triangle with each side length x, then the area of an equilateral triangle, standard formula, x squared root 3 over 4. We've shown already that in the second iteration it'll be 3 times 4 to the first, which is 12 sides. And then in that case, the area would be, well, you take the area of the starting triangle, and then you're going to have, as shown in the diagram, not to scale, 3 more equilateral triangles, so 3 times, and then this portion over here is the area of one of the smaller triangles. You split the base into 3, and then, so your side length is x over 3, quantity squared or 3 over 4. The same thing for when you have 48 sides. You would have 12 triangles with side length x over 9, and then you'd add everything that came before. X over 9 squared or 3 over 4. You use the same logic for when there are 192 sides. You take a third of x over 9, that becomes your side length, and you have 48 sides. Notice the times 4 pattern. Now we do some algebra. We take this expression here, and we factor out x squared root 3 over 4, leaving us with this here. Then what we do is we express the 9 as 3 squared and the 27 as 3 cubed. Notice that there's a dot 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 at the end. This is because the Koch snowflake has infinite sides. If we have a dot dot dot, maybe we can try to manipulate this so that we have some sort of a series that we can compute the sum of. So, in order to be able to do this, one of the steps we need is, notice that this 4 here, and then this 3 here, this 4, the exponent of this 4 is 1 less than the exponent of the 3. So if we can get, here it's also true because this is 4 to the 0 power, that's 3 to the first power. So then if we can get the exponents of the 4 and the 3 to be the same, then what we can do is we can put the 4 inside the fraction. So to do that, we multiply through by 4, and then we also divide through by 4. The multiplication is done inside the parentheses, division or multiplicative reciprocal on the outside. Then we can see 4 to the first, 1/9 to the first. 4 to the second, 1/9 to the second. 4 to the third, 1/9 to the third. And you may be wondering, this stuff changed. Well, in order for these two to have the fraction to have the same exponent, you can actually switch the exponent, because there's a 1 here, there's a 2 there. You can switch the 2 because the numerator is 1. Here, the same thing, and then here, 1 over 3 squared to the cubic power is the same as 1 over 3 squared, 1 over 3 cubed to the square power is the same as 1 over 3 squared to the cube power. Well, then we can just take this 4 here, for example, move it inside the fraction. And now this smells very strongly like an infinite geometric series, because 4/9 to the first, 4/9 to the second, 4/9 to the third, blah blah blah. So what we can do to get the infinite geometric series isolated, we can just factor out this 3. Ding ding ding! Infinite geometric series. We apply the formula, or you could use the fact that you already solved this earlier for this very same reason, and you found that it was the answer to this question was 4/5, and then you multiply it by that factored out 3 and you get 12/5. You do your arithmetic, and then you find that the area of a Koch snowflake with side length of the original equilateral triangle in the first iteration x is 2x squared root 3 over 5. Are there any questions? Thank you for watching. If you want to view this presentation in a digital format, please visit my website using the link shown on the screen. You have two choices for the activity. You can either play the chaos game or you can build your own fractal. Instructions for the chaos game are on the handout. If you're going to build your own fractal, I recommend that you first decide what your iteration is going to be and have a concrete idea of what it is. This will help you be structured and will make the overall process much easier. Again, thank you for watching.